You see my lecture, right? I don't
Yes.
see. I have to find it.
It's like the
Yeah,
miniatures of the slides.
it's very tiny.
Yes, I have to find it actually. Where is it? Here. You see this? You see me scroll up and down?
No.
No. Let me share it again. Close everything. Close this. Okay. Stop share. Now you see it?
Yes.
Yes. All right. So let me go to the start. So as we discussed already, now we want to take a step from the extratropical waves that we have been discussing so far, mostly. We want now to take a big step to the tropics, because also the tropics, they host very interesting waves, wave types, which we want to, some of them we want to discuss today. They are similar in many respects to the extratropical waves, but also have their own particularities. What you see here in this diagram is called what is a power spectrum. You are probably all more or less aware what a power spectrum is. So you take a quantity and calculate its energy, and instead of displaying it in the spatial space, that would be in this case time and just the zonal direction, you may Fourier transform that and display it in frequency and wave number space. Is just a different way of displaying things and very useful. In this case, the quantity that we are looking at is called OLR, which is standing for outgoing long wave radiation. The reason why this is very often used in order to try to understand waves and other behavior is that this is a quantity that is very easily measurable by a satellite. So we can have high resolution in time and space data that is just directly measured by the satellite. So this is just the radiation that the satellite measures. Now, why can we identify waves from this? The reason is, and you probably have noticed this in current weather already, maybe you're aware of this, that OLR can be used as a proxy for cloud cover, and particularly in the tropics, for cloud cover and rainfall. Can you guess why? Can someone guess why that would be the case? So when this quantity is large, that means the satellite probably sees very warm temperature close to the sea, let's say we are in the tropics, to the tropical sea surface, very far down. But when the satellite measures low temperature, since the temperature variations in the tropics horizontally, they are not very large, that means it must measure maybe the cloud tops. So low values of this OLR quantity means that probably there are high cloud tops, and most likely then also for in the tropics, that often means also convective rainfall and so on. So this quantity is then used also for as a proxy in tropical regions for rainfall, not only clouds. Now, it would be, from my perspective, it would be much better to look at a dynamical quantity, because the waves that we want to derive today are mostly dynamical waves. Let's say zonal wind or pressure perturbations would be much better to look at these waves. However, it's much more difficult to directly measure, for example, zonal wind. So therefore, people like to use this quantity OLR. But of course, we can use this quantity because the waves that we will derive today, the way we derive them, they are simply dynamical quantities, so mostly related to just zonal wind and pressure perturbations and maybe meridional wind perturbations. But we don't talk at all today about how they are related to convection. However, in reality, it turns out that these waves that we are deriving today, they are often related to also tropical convection. So with these waves that are propagating, we also have a propagation, fast propagation in this case, of tropical convection. And that's why we can use, and cloud cover also. So that's why we can use this quantity OLR also to measure these waves, which are, however, in reality, at least from the theory that we will derive today, mostly related to just dynamical fields and not related to tropical convection. But in practice, they are also related to tropical convection. So the red colors here indicate where we have an increase of this energy in these waves. And this is a wave, a power spectrum averaged for the equatorial region. So 15 degrees south, 15 degrees north. So we average out the meridional direction. So we just have the X and the time dimension. And then this is transformed into spectral space. So we have something like, we can identify something like our dispersion relationship, because we have the energy expressed in terms of frequency and wave number. And indeed, there is this special wave type that has most of the energy, which we will derive today. This is very red here, which is called this Kelvin wave. And if in this diagram, frequency and wave number, they are just proportional to each other, so there's a linear relationship, then that means that these waves are non-dispersive. Because if we divide the frequency by the wave number, we get the phase speed, and that would be just constant. So these waves here, they would be eastward propagating. And this is one of the wave types that we will derive today. And then there are westward propagating waves. They're slower. The fact that they are more down here, less slope, means that they are slower. And they have a more complex dispersion relationship. And there are some more complicated waves up here. And there's something down here. There's an energy increase down here at wave number 1, 2, 3. So these are zonal wave numbers. So around the whole zonal direction, we can measure for this, what is called Kelvin waves here, wave numbers 1 to 5 and so on. But for the waves here, we maybe have wave number 1, 2, 3, and they're extremely slow. They're very slow compared to the Kelvin waves. That's the reason why they are down here. Can any of you guess what these waves are? We will not discuss these waves here, the waves down here, in details. But these waves are extremely famous. It's actually called oscillation. It's not it's a wave propagation, but the name is referring to an oscillation.
The ENSO?
This is not ENSO, but it could be, because ENSO is also something that is probably very slowly evolving. But this is actually called the Madden-Julian oscillation, which is related to ENSO somehow. ENSO can modify this Madden-Julian oscillation, or the Madden-Julian oscillation may modify ENSO, but it's a very slowly, just atmospheric propagating wave that moves around the globe. We will not discuss this because the theory behind this Madden-Julian oscillation is not so well established. It is, there are still many scientific publications on how this wave is actually established. So it's essentially it is related to the Kelvin waves also, but it's a clustering of convection that is very slowly propagating, and the theory for that is not so straightforward as it is for Kelvin waves and the other waves that we see in this diagram. But it's a very famous wave that we will not discuss. I just wanted to mention it. So usually this increase of energy down here, very slowly propagating in this diagram, is referred to as the energy related to the Madden-Julian oscillation. Now we can look at this actually in a slightly different way, not referring to this Fourier transformation where we look at frequency and space, frequency and wave number, but here we look at time and space. So imagine this is now from a model, from a numerical model, because we can do idealized things. What we can do in a model is we can impose at one time, for example, in this case, a sea surface temperature perturbation that will cause convective events there, in this case in the tropical Atlantic. We will discuss this later, maybe in the next lecture. Those waves will hit the tropopause, the vertical motion will hit the tropopause and will lead to wave propagation near the tropopause. And this is what is shown in this diagram down here. Again, averaged over the equator in a more narrow band. But the quantity that is shown here is much more dynamically relevant, which is the U, the zonal velocity, at this 200 hectopascal level, which is close to the tropopause, let's say 10, 12 kilometers. And then we see here, these colors here mean that positive U velocity is indicated with red colors. So these waves or this vertical motion that hits the tropopause and initiates waves there, this energy is propagated in the zonal direction with a certain phase speed, which should be related to the phase speed of the Kelvin waves, because these waves are those waves that propagate in this positive x direction. And then we have also waves that propagate in the other direction, here indicated by this negative velocity. And this envelope here indicates us the phase speed. And this phase speed, as you can see, is much slower. Now, there can be many reasons why this is the case. There could be some Doppler shift. There could be just some mean flow that causes this. But we will see that these waves are very different type of waves, probably. So there's a reason why we expect that they have different phase velocities. But this is just another way of displaying this energy propagation. Once you have an energy source, then these waves are propagating along the tropics. And as you can see, this goes relatively quick. This is a switch-on experiment. So at day 0, which is down here, we switch on, and then you wait essentially not even 2 weeks, and this whole energy is propagated around all everywhere at the equator. So this is a relatively quick wave propagation. It just takes a few days for it to propagate essentially all the way to the Pacific. And we want to understand this a little bit more. So in order to derive the basic equations, this is now probably useful for one of the exercises where we want to repeat the derivation of the shallow water equations that we have used already before. But when we discussed this our barotropic model for the Rossby waves, We have used this set of shallow water equations already, but here we just want to systematically derive this set of equations again. We need 3 assumptions for this model. One assumption is that the density is constant. This is a very, very stringent assumption for the atmosphere, of course. For the atmosphere, this is not valid, but sometimes if we only consider very small vertical perturbations, maybe it can be an approximation. Then the flow should be relatively shallow, such that the horizontal velocities are independent of height. And the flow should be hydrostatic. Hydrostatic, okay, we always assume that our flow is in the large scale is hydrostatic. Then we can write down our momentum equations again. We have seen these equations already. These are our horizontal momentum equations. The Euler equations, again, without friction for simplicity. And the vertical momentum equation, which degenerates to the hydrostatic equation. And we have the continuity equation, which, of course, with the density being constant, simplifies. We get simply the divergence of the wind is equal to 0. Simplification of this equation here. Now, the exercise, I think the exercise number 3 of the first lecture was to derive the pressure gradient force in terms of height changes of our system, because the shallow water model is very simple. We have let me try to draw it here. The idea is kind of to have a basin, and then we have a free surface. And this can have the total height from x, y, and t. And the perturbations of this height will govern us the pressure gradient force within this layer. And that's the idea, that we can replace this pressure gradient force by the perturbations of the height. We can derive this law by integrating the hydrostatic equation from an arbitrary height, z. That is the trick. We have to identify just some arbitrary height, z. And we integrate from this arbitrary height within this medium. It can be the surface, but it doesn't have to be. It can be any height within this system, and we integrate the hydrostatic equation from this arbitrary height to the top. So if we do this integral of this hydrostatic equation from this arbitrary height z to the top, where the top can, of course, depend on x, y, and t, and we do this on both sides, then we have the pressure at the top minus the pressure at this height, z, which of course can also then depend on x, y, and t. And on the right-hand side, we can make use of the fact that g is, of course, for us a constant, the acceleration due to gravity, the density is a constant. So this is just multiplying by the difference between the top and our height z. So this is just h minus z. So the vertical dependence of our pressure becomes very simple. It's just a linear combination of this height that is dependent on x, y, and t, and the z. And that makes it so simple. And of course, now we see immediately that if we apply d by dx derivatives here, then the z dependence drops out, because dz by dx is 0 in this. No, z is an independent coordinate. It's independent of x. So So we get this simplified system where we can express the pressure gradient wherever we are in our system here as the gradient of the height of the surface. We just have to measure this free surface height. Then we can express this also as the geopotential. So we can insert this as the pressure gradient here. And this is what is done here. And that was the meaning of the exercise. So it can be done in a formal way, just like this. And then you see already that the pressure gradient force is independent of height. So you could also integrate from zero, from the bottom to the top. And then its pressure gradient would also be valid at the bottom. And so this becomes our horizontal momentum equation. And then in order to close the system, we need an equation for this G times H, for the height of our system. Of course, intuitively, we know already, whenever we have a convergence of mass in our system, the height should go up. And if we have divergence of mass, the height should go down. So the continuity, the mass continuity, tells us how this height of the system should behave. Now, formally, we can simply integrate the divergence-free relationship. Whereas here now, maybe this is not consistent. There should be, these are just the horizontal components of the velocity. And here we have split off the vertical component of this, the vertical part of the total divergence. So we can integrate this equation in the vertical direction again. From, in this case, it's convenient to integrate from 0 to the top. Then we get the vertical velocity at the top minus the vertical velocity at the bottom. The vertical velocity of the bottom, if we don't have topography, is 0. But the vertical velocity at the top is just, the definition is just the total derivative of the height of our system with time. That's the definition of this going up and down. That's the vertical velocity at the top. And so on the right-hand side, since the horizontal, according to one of our assumptions, the horizontal velocities are independent of height, this integration is just the multiplication of the divergence times the height. So if we multiply this by G, we get to our continuity equation as we are, if we have used this already. So this is now our set of basic equations. And this set of equations we have already used to derive extratropical inertia gravity waves. Do you remember? We have linearized this in a setting where we said, okay, the mean velocity should be 0, and the Coriolis parameter at the base point where we are is a constant. And then we could derive our inertia gravity waves, and the waves that we found was, let's say, C equal to plus or minus square root of F over K square, F square, I think, plus G times some kind of the height, the total mean height of our system, sorry. So this was the dispersion relationship for our inertia gravity waves in the exotropics, which is a gravity wave kind of mixed with this inertia behavior. And we have said already that this, if we take for H the total height of the tropopause, these waves would be extremely fast. So 300 meters per second. Extremely fast waves. Now, we want to do the same linearization that we did then, now for the tropical regions. Exactly, strictly speaking, we want to put our base point at the equator. But this immediately brings in a difficulty, because the Coriolis parameter goes with, as you remember, goes with the sign of the latitude. So our Coriolis parameter base value is F0, would be 0 at the equator. So when linearizing our set of equations, the only term that could be considered is this beta, this change of Coriolis parameter with latitude times the latitude. So this is the only term that can be relevant, because F0 is 0 at the equator. So our linearized equations look like this. And we have introduced here some kind of scale height HE, which for the atmospheric waves that we will consider here right now, this scale height, we will derive, there's no physical meaning in this, but we will derive this height by later on identifying what are observed phase velocities for the waves that we identify. But for the ocean, of course, we will see that this height has a physical meaning. And for the waves that we will derive probably in the next lecture along the equatorial thermocline, then this height HE would be the depths of the thermocline. If you don't know yet what that is, doesn't mean, but anyway, that is the active layer of the equatorial ocean region where also Kelvin waves these equatorial waves can develop, and that has to be considered. And then that has a physical meaning. But for the atmosphere, we have simplified the system so much that this height has to be adjusted afterwards in order for these wave perturbations that we derive to make sense. So the system of equation that we have looks again very simple, but we have a problem, because so far all the waves, the extratropical Rossby waves, the inertia gravity waves and the extratropics, all the waves that we have been deriving have been derived from a system, a linear system, homogeneous linear system of equations with constant coefficients. But now, this beta y term means that our coefficients are not constant anymore. That makes the solution of this system a little bit more complicated. Now, who's good in math could probably solve this equation without any problems anyway. What is usually done in this case is that it is assumed that there is a separation of the y dependence, which is a special case here, from the time and x dependence. And we try to find solution of this type. It turns out it will be successful. So you can just dream that the solution should have this form. And then if we find the solutions of this form, then we have solved the problem. So we assume that there is an amplitude function that just depends on the meridional direction. And the waves themselves, they propagate in zonal direction. This makes a little bit of sense, because since we have said our base point is the equator, we can't go anyway. Our waves shouldn't leave too far from this base point. Otherwise, our basic equations would not be valid anymore. Our F0 would not be 0 if we are going too far away from the equator. So we have always to stay relatively close to the equator. So it wouldn't make sense for our waves really to propagate too far away from the equator. So it's now very easy. If we insert these perturbation quantities in these equations here, we know immediately how to do this. In some cases, if the derivatives are respect to x or with respect to time, We just get again our wave numbers and our frequency down. But sometimes we have to take into account also the derivatives of these amplitude functions, d by dy here. So we have to retain this derivatives d by dy here for the geopotential, for the height, and for the meridional velocities. And then we divide again by the Fourier component. And what we get is this system of equations, 3 equations, coupled equations, linear, but still with non-constant coefficients, for our amplitude functions, for our amplitudes and we want to solve this for our amplitude functions. Now we can insert, in principle it's straightforward, we just insert one equation into the others here, and for example eliminate the u component between 2 of them, and then we get these 2 set of equations for the meridional component of the velocity and for the height, or g times h here. And we can again combine these 2 equations in order to derive this equation here. So we eventually we can just derive one equation for the meridional velocity component, and that is this equation here. Now this would be a very simple equation if it wasn't for this term here that depends on y. If that term wasn't there, this equation would just be would have oscillating solutions or exponentially decaying or increasing solutions from the equator. But for this term here, this set of equation becomes more complicated, and we need to be careful to solve this equation. Now, what we want to look for is always solutions that become small if y becomes large. So we want to have decaying solutions if y becomes large, because we know that our solutions will not be valid. Different solutions different from 0 will not be valid if we go too far away from the equator, from the space point. Now, clever mathematicians have identified that this equation has only solutions if this bracket here is an odd number. So this bracket here, which can be written in this form, has to be an odd number. Then this has solutions. And this is now a dispersion relationship, because if we insert 0, 1, 2, and so on in this equation, we get relations between our frequency and the wave numbers. So this is a form of a dispersion relationship. It makes no sense. It's just a substitution to substitute our y, our meridional distance to the equator, with some scaled quantity, which we call xi in this case. It's just a scaled quantity that is then, it turns out to be dimensionless. You can just take it as it is. It makes this new distance from the equator to be dimensionless. And then using that, this equation becomes this equation here. Now, those of you who studied a lot of physics, I studied a little bit of physics, in particular quantum mechanics, many years ago, and then not so much anymore. But maybe for you, some of you, this is still fresh. So this is a well-known equation for quantum mechanical harmonic oscillator. And so this is often what is often done. If we manage to reduce a system to something, a system of equations, to something where we know already solutions, then we are done. Now we have reduced our wave equations in a way that we reach a form that is where we know the solutions already from another field of physics. Then we have solved the problem. And it turns out that the solutions of these equations, depending on the n that we insert, are Hermite polynomial. So you can also say this is for each n that you insert here, n equals 0, 1, and so on. This is a defining equation for Hermite polynomials, because if you insert this into this and solve for the h0, h1, and so on, you will find that these solutions here just solve this equation. This is the defining equation for Hermite polynomials. So the solutions always look like some polynomial, which can be either just one or have one node if it's just proportional to this scaled latitude, or if it's proportional to the scaled latitude square, it has two nodes. But then there's always the exponential. So these waves will always decay. If we go far away, the exponential will always win. If we go to infinity, this will always go to 0. But then there is, as we are close to the equator, there is some structure which is defined by this polynomials. So this solution become quite complex. Now, we are looking in more details at this case, n equal to 0. For n equal to 0, this becomes equal to 1, and this dispersion relationship factorizes in this way. You can work it out. Just multiply this by this. And then it turns out that you can write this equation, this factorization, which is always useful. Now, one of the roots here, so either this is 0 or this is 0. This is one solution, which is shown here. But this corresponds to a westward propagating gravity wave, in this case, westward, because it's a negative zonal direction. But this was actually not permitted, because when we derive the set of equations, initially we have divided by this quantity, by inserting one in the other, and so this was excluded as solution. So this solution is not be there, because we have divided by this, essentially. And so the only solution that can be relevant is that this is 0. And that would be the dispersion relationship. And so this is still a quadratic equation. And the solutions, if you can work this out, if you set this to 0, are given by this. Now you see, this is a very, very complex dispersion relationship. It's clearly highly dispersive, even though there's this term here that really looks like a gravity wave component, but then there's a square root here that contains all kind of rotational effects. The beta effect is here, so the fact that we have the rotation of the Earth comes into play. So therefore this is called mixed Rossby gravity wave somehow, because we have components from the gravity wave and components from our Coriolis parameter that changes with latitude. Now, for large wave numbers, this could be identified as 1 plus a small quantity. So if we have the square root of something 1 plus a small quantity, then this is approximately in the first order Taylor series expansion, 1 plus 1/2 x. If you do that, then if x is small, then if you look at the positive, then you can ignore this quantity, which we may call x here. Then it just gives us a gravity wave, because we have 1/2 plus 1/2, and so that would be just so the positive root here would be a gravity wave, eastward propagating gravity wave. But the negative root, then this 1/2 goes out with this value, and what remains is the 1/2 of this quantity, which we call x. Now 1/2 of that, and there's another 1/2 here, it turns out, and then you divide this by g times h, but you multiply this by g times h, it turns out that this is just the only thing that remains is nu for this negative solution is equal to minus beta, sorry, beta divided by k. So in this limit for this westward propagating wave, in the limit for large wave numbers, we get what we know already is a Rossby wave, because this was for zero mean flow. This is the dispersion relationship for Rossby waves, because if we divide this by k, which is the phase speed, then we get our dispersion relationship for Rossby waves for zero mean flow. So this tells us that in the limit for large wave numbers, so if this quantity here is small, then we get really this distinction of two wave types. But if that is not the case anymore, we get really a mix of waves that are more like gravity waves or waves that are more like Rossby waves. So this is this mixture of inertia gravity and Rossby waves that we get. We call them also Rossby gravity waves. So there is now a very, very important, as derived from observations, and we have seen this, there was this wave type that is very powerful. You see this, the most powerful wave is a purely eastward propagating gravity wave. That is, however, called Kelvin waves. That is called Kelvin wave, and there's a reason for this. So you haven't started the ocean course yet, right? No. But have you heard already about Kelvin waves in the ocean? The Kelvin waves are a very special type of waves that rely on the fact to have a border, because then you get, then one of the velocity components becomes zero and you get an increase of wave amplitude at that border. So you can observe this in your bathtub. When you create waves, they tend to be maximum at the border, and then they may propagate around the border of your bathtub. Those are Kelvin waves, but they exist also in the large scale, of course. So they need typically, Kelvin waves typically need a border that guarantees us that some velocity component is zero. Now, in the atmosphere, we don't have typically borders easily. In the ocean, it's clear. At the coastal regions, we have some kind of borders, but in the atmosphere, that's not the case. But the equator can provide something that is similar to a border and makes the wave energy to accumulate at this imaginary border, which is the equator. So the simplest way to derive this Kelvin wave is simply we assume that the meridional velocity component is 0. So we have only zonal velocities. So that is our border idea, essentially. There's no meridional velocity component. And then our set of equations, and we can try to solve them for that special case. If we set in this set of equations the meridional component exactly to 0, then this term drops out, and this term drops out. And this drops out. So we get a simplified set of equations, which is this set here, where all the meridional components of the velocity have been set to 0. Now, if we eliminate between these two the phi, we get the dispersion relationship immediately for Kelvin waves. And it's not a surprise. We have seen that already. They look like straight lines. So their dispersion relationship is the one of a gravity wave. So nu over k square c square is equal to g times h. This is a gravity wave. In principle, from this dispersion relationship, the waves could still propagate in positive or negative zonal direction. But it turns out if you manipulate this set of equations in a different way, such as to eliminate d phi hat by dy here, you get to this set of equation, just one equation, which you can easily show by inserting the solution of this equation is this one here so it's an exponential with y square in the exponential. So by deriving this with respect to y, you can see that this is fulfilling this equation here. Now, if this is the solution, then we can, however, work out that from these two possible solutions here, only the one with positive phase velocity is reasonable, because only that one will have decaying solutions away from the equator. The solution where we take the negative square root, that would be a negative c, and then our solutions would increase exponentially away from the equator. So that is not reasonable. So we have to remove that possibility as a solution. So our Kelvin waves have to have always positive phase velocity in zonal direction. So they always propagate to the east. That is this special type of waves. And it turns out that this wave is the most powerful equatorial wave that we can actually observe if we look at those power spectra that we have been just looking at. So you can also derive how fast do these waves decay away from the equator. But you have to insert a phase speed. Now, if you take this phase speed here, this is just an observed value. This is an observed value derived from, for example, from this dispersion relationship that we can find here. This would be a typical value that you can derive from this diagram here. That is the typical phase speed of the waves here, the slope that we see here. Or you could also take this, the propagation speed that we see here. That's typical propagation speed for atmospheric Kelvin waves, 30 meters per second. So quite fast. much faster than the typical speed of the Rossby waves that we have been looking at, for example. Now, interestingly, of course, if we insert this, so this value we cannot derive from the equation themselves, because in order to derive that, we should insert a value for this scale height that we have been using. If we work out what is the scale height that corresponds to the 30 meter per second phase speed, we would come to 100 meter. Now 100 meter for the atmosphere, there's no real physical meaning that you can assign to this quantity. Whereas, as we will show in the next lecture, for the ocean case, yes, this quantity, the scale height, has a physical meaning, and it's also slightly more complicated because we have to make use of this fact that in the ocean we can identify this thermocline, but there's a physical meaning attached to it. For the atmosphere, it's very difficult to identify any physical meaning of this. So we get back to, we have used a hammer to modify our atmospheric equations in such a way that we can find analytical solutions. And they turn out to be very useful because, in fact, we can find these Kelvin waves that are very much observed in the real world. But then to identify a physical meaning for the scale height is not easy, cannot easily be done. Now, how do these waves look like? Now, here are two examples. This would be here the Rossby gravity wave down here, and this wave here would be a typical example of a Kelvin wave, where we have only zonal velocity components. And these are the lines of pressure, lines of constant height of our systems, are also lines of constant pressure, which should be proportional. But you can also see from this equation here that where the height is maximum, then we get also the maximum of the zonal velocity. So they are proportional to each other. So where we have the maximum height of the system, we get the maximum zonal flow. And then if that is negative, then the zonal flow has to reverse. Now this structure gives us an indication for the consistency of this eastward propagation, because if you imagine now that we are at the zero line here, at the zero line, these flow components indicate us that we have a divergence. So mass is lost here in principle. So the way to do this is then to propagate this wave over, because here we have the negative height perturbations. And if they propagate over, we can kind of intuitively understand why the waves are only propagating in the positive x direction, because that is consistent with the divergence field that is associated with the u component identified here. So these waves are indeed, as we can see here, the most powerful waves that we can find in the tropics. And we come back to this again. So now we have seen that, yeah, in order to find these waves, we should best look at for example, zonal wind component or the pressure field from what we have derived. But the data that we are using here, as you can see, is this OLR, which, as I told you, is the only physical relationship that we could find is that we can identify this as convection, tropical convection. So clearly the waves that we identify here, they must be all related also to tropical convection. So as these waves propagate, they also lead to tropical convection, and we can identify them in this way. So let's make a 10-minute break. and then we start the next lecture a little bit. Okay, so see you again at 12:05. Hello. I will start to share my screen again. Can you hear me? Okay. So the waves that we have just derived, they will be very useful to discuss this ENSO atmosphere and ocean feedback mechanisms. You all have heard about ENSO, right? It's such an important phenomenon. Everybody has heard about ENSO. And the reason why we are discussing this here is, okay, it's part of the ENSO, of course, is as you may know, an ocean atmosphere coupled phenomenon, one of the only quite well understood ocean atmosphere coupled phenomenon that they are. And it's so important because it has these global teleconnections that may influence temperature and rainfall all over the globe, and is really the only reason we have right now to believe that there can be any forecast possibility potential at seasonal timescale or longer timescale. It's based on this phenomena. Now, and we will see that the waves, these equatorial waves, they will be very, very important to understand the feedback mechanisms for this phenomenon and also its propagation of information in other regions in the ocean and in the atmosphere. So we can look at this picture here, which is an anomaly of one particular day. This was in autumn, 26th of November 2015. So this was the development of the last big El Nino event that has happened in the year 2015-16. I don't know if you remember, but there was one of the biggest El Nino events, maybe similar magnitude than the one that happened in 1998, 1997, 1998. And those two events were the biggest events in the recent history. And of course, there were global climate and weather perturbations related to this event. Now you can see the fact that it's possible to look at this event by looking at just one particular day tells us already that the sea surface temperature perturbations that we see here, they must be extremely persistent. It's not that they are one day there, the other day they are gone. No, they have a huge inertia. They are there all the time and then develop slowly, may increase slowly and slowly decay. Now, what is an anomaly? So anomaly for this day means that we are looking at the sea surface temperature of that particular day and subtract the long-term mean for that particular day. In this case, long-term mean means rely on a climatology that is typically taken from 1980 to 2010 or 2015 in this case. And we collect this long-term climatology by averaging the temperatures for this particular day and do the difference. And then in this case, you can see that on that day, the sea surface temperature perturbations, the anomaly with respect to this long-term mean was up to 4 degrees in some regions. In a large region of the tropical Pacific. So you can imagine that this must have some influence on the atmosphere that is on top of this, that must perturb the atmosphere locally, but as we will see later, also globally in principle. So let's see if we can have a more detailed look what is actually going on, what interesting features are going on in the equatorial tropical Pacific. This figure here shows us on the equator. So we are on the equator here, a section that goes from the surface down, in this case, to 500 meters, and from the essentially Western Pacific here to the Eastern. So this is the coast of, here on the right would be the coast of South America. And then here we are somewhere in the Western Pacific. And if you look at the structure of temperature here, so the red means warm temperatures and blue means cold temperatures. This almost looks like what is going on right now in Trieste, I think, because we have warm temperatures at the surface and cold temperatures as we go down. So exactly the mirror picture of the typical picture that we have in the atmosphere, typically, where the temperature typically is decreasing with height, as we know. If we go to a mountain place, we expect it to be colder than it is at the surface typically. But in the ocean, we have typically the opposite situation. One reason for this is that the ocean and atmosphere, they are both heated at the surface in principle, where the solar radiation hits the surface, then that heats the atmosphere and that heats also the ocean. So it's not surprise kind of that, okay, we have the warmest situation at the surface perhaps. But if we go down, look at this. Even only at 500 meters, we go down to 9 degrees. Now this is for me, as not being an oceanographer, maybe for oceanographer this is so trivial, but for me, this is very surprising. And if we go down even further, we could go down to a few kilometers. We would go down to 4 degrees perhaps. 4 degrees. So how is this possible? And can you think of any reasonable physical explanation why we would have so low temperatures at the equator? For me, this is extremely counterintuitive, because I would assume as a simple physical process, if we have the temperature that we have near the surface, that should diffuse, given the long history of the Earth, should diffuse somewhere down, and we would expect maybe more or less similar temperatures at the bottom of the ocean, but that's not the case. What do you think? How can that be? Just make a guess. Well, how can it be at the equator? I mean, there's not a fridge or something like this, right? There's no simple explanation why. So there must be, the only explanation must be that there must be a very slow but very efficient, compared to the diffusion that is certainly going on also, not so efficient, but there must be a very, very slow but efficient overturning circulation that somehow brings cold extratropical water down to the surface of the equatorial Pacific. I mean, you will discuss these kind of circulations that are related to this global overturning circulations of the ocean. You will discuss them in the oceanography course, of course. It is not up to me to do this, but for me, this is extremely counterintuitive. And of course, oceanographers, they will have names for these kind of water masses that are lying very deep in the ocean. And even at the equator, they can be extremely cold, which is, for me, very counterintuitive. But this brings us to this very, very interesting situation where we have this cold water down here and the warm water at the top. It's interesting because then, since the ocean has circulations, also vertical motions also, then in some regions, like maybe it's suggested here at this, close to the east coast of South America, where we probably have rising motion in the ocean here, this cold water comes closer to the surface than in the Western Pacific. And so if we look at a picture now in the latitude and zonal direction, this is for July, but it doesn't matter. We could also look at it in the, for example, January. The picture would look very similar. We have it is warm in the tropics and cold in the exotropics. But focusing on the equator, we also see that in this eastern part of the equatorial Pacific, we have these cold surface waters. You see that? The same is also true for the Atlantic. So there must be intuitively, I mean, if you look at this, it must have to do with somehow with the vicinity of the coasts here, right? Clearly, it must be something, because that is missing here. We can simply think about it. So intuitively, we can make a simple hypothesis why this is going to happen, because we know what do we know? What is the mean wind direction in this region here? I'm lucky I can even draw. So what is the mean wind direction? What type of winds do we have in the tropical regions on average? Do you know? You're muted.
To the left.
Westerly wind.
Westerly? Westerly would be, okay, let's say we would have high pressure. I cannot draw on this. Wait, let me see. We would have a high pressure. This is not very nice. But let's say sitting here, maybe that should be further to the north. So at around 30 to 40 north. And indeed, to the north of this, we would have westerlies. But to the south of this, remember our geostrophic balance? How the air moves around a high pressure system? Has to move in a geostrophic balance in a certain way. To the south of these high pressure systems, that is also in the Atlantic actually, we have flow that goes from the east to west. And because of surface, and the same is true for the southern hemisphere. Because of the surface friction, because we have on average a lower pressure at the equator, then that would be these, we call them northeasterly trade winds. So you get winds that actually blow somehow into the low pressure at the equator. So we have easterly, in principle, if we think of zonal wind direction, we have easterly winds. Now, that will cause a problem for the water masses, of course, at the coast here. Because if the water is transported over at the surface, where the surface flow will be kind of dragged by the wind away, that causes a problem here because we lose water. So this water that is lost here has to be replaced by something. And it can be replaced, of course, by water that is coming from the south and from the north, but it can be also replaced by water that is coming from down, this upwelling. So we get this coastal upwelling there, in principle. That is partially triggered by these trade winds, but also by the wind systems that are then developing around the coasts here. So we get an upwelling close to the equator here. And so that cools off the surface waters. We get actually so cold water that it's almost impossible to swim there. So it's like around just a little bit more than 20 degrees. So it's on the equator, extremely cold. Very counterintuitive for someone like me who has never experienced something like this. And so that is going on. There's actually a reason why, in general, on the equator, you may have the tendency for cooler water because of this upwelling, maybe a little bit happening everywhere on the equator. This is because of Ekman pumping. Because if you remember, I don't know if you discussed this yet, but if we have these easterly winds, that will cause in the ocean a flow, Ekman flow, that goes to the north, in the northern hemisphere, and to the south in the southern hemisphere. So on the equator itself, there will be always, given the trade wind situation, the tendency for upwelling. But that upwelling, how efficient that is, that depends on the depths of this thermocline. So if this, we haven't discussed yet what the thermocline is, but we can discuss this here. So the what in the ocean is called thermocline is kind of an idealized line between the warm surface water and the cold bottom water. It's not just the thermocline, that would be something like in the atmosphere, the tropopause or something like this. So there are several definitions. I think the most physical one would be to look for the strongest gradient here, the strongest temperature gradient, and then call the surface water would be just the water that is up here, and the bottom water would be kind of this more inert layer down there. But I think in practice, people also pick just the 23-degree isotherm and say, this is the typical situation, this is a typical thermocline position. But of course, then if you have a warming climate, then this 23 degrees may not be representative anymore. So that may depend on the situation. But this thermocline is kind of this region of the warmer surface water. And as you can see in the Western Pacific, that goes quite deep, so 150 meters. So even though you may have some weak upwelling given by this Ekman flow close to the surface, but that won't bring so cold water up. Whereas at the coast here, at the South American coast, it's very easy to bring up cold water. So that is this very strange situation. Kind of, we can guess already that this is a situation a little bit under tension, because if we remove the trade winds, then what we will expect is that the warm water is flushing all over the place again. This thermocline probably goes away, and we get everything is warm. The thermocline is flat and everything is warm situation. That this kind of probably more normal situation from some point of view, that is called El Niño. That is happening during these events when suddenly, in anomaly terms, it looks like this. But if you look at absolute terms, that would be just mean that the whole equatorial Pacific is flushed with warm waters. Because in this region where you have this particularly a little bit unusual cold situations, however, on average, then during these El Niño periods, then we have the maximum of the warm anomaly exactly in that situation, in that position. So the warm water is flushing all over the Pacific in El Niño conditions. Maybe we have a picture of this. So this would be the typical La Niña situation or normal condition, where we have these trade winds are indicated here. We have most of the convection sitting over the warm waters, And then we have something that is called Walker circulation we will discuss this later in this course. But essentially, these trade winds that push over the water to the west make that this thermocline is tilted in principle. And then during El Nino, this is the picture here, then essentially this whole system under tension breaks together, but just for months to a few years until it builds up again, because eventually the trade winds will win again. But for some time, we can have this situation that the warm water is flushing the whole Pacific region. And the convection moves from the Western Pacific maybe to the Central and even Eastern Pacific, depending on where we are, how strong also the ENSO event is. And the thermocline becomes much flatter than it used to be. So we get to some situation that somehow, for some intuition, is actually more what we would refer to the normal situation. The whole Pacific is just warm during these El Nino events. And so in the next lecture, we want to discuss this further. It's first of all, it's possible teleconnections and what is going exactly on when we have a warm patch in the Eastern Pacific here. But then we want to understand the positive feedback mechanisms in the atmosphere and in the ocean that makes this El Nino phenomenon maintain for some time before it weakens due to other negative feedback mechanisms. So I will discuss this in the next lecture on Friday. And today we are finishing, okay? Fine. So whenever you have some doubts, some question, you can send me this in the Slack, and then I may look at this from time to time. Okay, thank you, bye.
Thank you, bye.
Visto che non sei ancora andato, ma com'è la temperatura?
Non ti aspetto, ma mi finisco di... Quali cose, scusa? Tu hai questo? O preferisci la mascherina? Questo, magari... Parlo di Gaia. Abbiamo anche un altro adesso.